In a steady hover, a UAV is engaged in a high-frequency physical argument against gravity and wind turbulence. Its airframe must tilt and roll hundreds of times per second to counteract forces that would otherwise push it off course. Holding this stationary position requires constant sub-millisecond calculation. The system cannot simply lock the motors at a static speed. It must modulate thrust constantly to stay still. This stability requires a high-speed signal flow architecture capable of processing these environmental corrections in real time. This flow follows 3 stages: the ingestion of raw data, the mathematical calculation of error, and the physical actuation of the motors. To understand this system, we will trace a single command signal from the origin of operator intent down to the physical rotation of a motor and back again. This flowchart details the software architecture that governs the sequential logic flow, mapping the specific algorithms that keep the aircraft airborne. And this circuit diagram maps the hardware architecture, the physical pathways and distinct electronic modules that route and execute those algorithms. Mastering both the algorithmic map and the physical schematic is necessary to grasp the mechanics of closed-loop control. Autonomy exists as a continuous cycle of microscopic corrections, maintained at a speed that permits no deviation from the pilot's intent. Every action begins as an intent, whether it's a pilot pushing a joystick on the ground or an onboard AI generating a new mission waypoint. On the signal flowchart, this intent enters the logic stream through the AIOS block or the communications link. From there, the command pocket is routed directly down into the central processing unit, the flight controller. In control theory, this incoming command is the set point, the mathematical goal the drone has been instructed to achieve. Before the drone can calculate how to move toward that set point, it must determine its current exact position in 3-dimensional space. Switching to the hardware schematic, this spatial data is gathered by the sensor suite, specifically the gyroscope, accelerometer, and GNSS modules. That raw telemetry travels back up the sensor buses, feeding directly into the flight controller. Raw sensor data is noisy and often contradictory. It must be mathematically filtered before the data is useful for navigation. This critical mathematical filtering step happens inside the state estimation block. Here, a sensor fusion algorithm blends the noisy inputs into a clean, unified matrix that defines the aircraft's exact position, velocity, and attitude. A drone can only correct its flight path if it possesses an accurate, real-time mathematical model of its own physical state. Now that the system has a target set point and a current estimated state, the logic stream must reconcile the two. The mathematical difference between where the drone is and where it wants to be is defined as the error. This error is processed in the flight control logic block. Inside this block, PID controllers calculate the exact aerodynamic force required for altitude, position, and attitude correction. This calculated corrective force is abstract. It cannot directly spin a physical motor. The abstraction is translated into hardware instructions below, in the motor mixer. The mixer takes the combined demands for roll, pitch, and yaw and splits them into distinct thrust requirements for each individual motor. Those commands are then serialized into digital protocols like DSHOT, ready to leave the logic processing stream. The flight controller translates high-level spatial geometry into low-level electrical instruction sets. With the digital instructions finalized, the system transitions from mathematical calculation to physical execution. These sensitive, low-voltage logic signals must now interface with massive electrical currents to spin the propellers. On the hardware schematic, we track the egress point, where these signals leave the flight controller via the motor out pathways. The signals route directly into the actuation systems block, arriving at the 4 electronic speed controllers, or ESCs. An ESC reads the incoming low-voltage pulse and uses it to modulate the flow of high current power driving the motor. Cautionary tone. High current power creates massive electromagnetic interference. If that interference reaches the logic circuits, it can corrupt the telemetry. The architecture solves this via modular separation. Thick red lines route high current power from the distribution board directly to the ESCs, isolating massive loads. This contrasts with thin, yellow pathways delivering regulated power to sensitive electronics inside the flight controller. Strict physical and electrical isolation between logic circuits and power distribution is mandatory to prevent electrical noise from crashing the aircraft. As the motors receive their power, they generate thrust and alter the aircraft's physical trajectory. The drone physically banks through the air, correcting its error and closing the gap to the commanded set point. The millisecond that movement occurs, the mathematical state estimation the drone just calculated is rendered obsolete. This new physical reality is registered at the bottom of the flowchart as the flight result. That updated spatial data flows back up the feedback loop to the sensors. The IMU and GNSS ingest the new positioning, immediately feeding it into the sensor fusion block, and the entire control logic process restarts. This continuous circuit, sense, decide, act, fly, repeat, is the closed-loop control system. To maintain flight, this loop must execute hundreds of times per second. If latency is introduced, whether from a slow processor or electrical interference, the drone will fail to correct its error, resulting in catastrophic oscillation. UAV autonomy relies on the precise, high-speed synchronization of rigorous hardware isolation and mathematical control theory.